Dear learners, let us do the analysis of continuous beam ABCD by slope deflection method, and based on the results we can able to find the bending moment, and finally we are going to draw the bending moment diagram. So for the given beam we have to take the flexural rigidity EI is going to be constant throughout the entire length of the beam. So now we can see a continuous beam with three spans, namely AB, BC and CD. So AB, one end is fixed, the other end is hinged. It is supporting a concentrated load of 100 kilonewton. Span BC is 5 meter length. It is completely loaded with UDL, and span CD is overhanging, and it is provided with a 20 kilonewton load at the end. So this is a continuous beam. First we have to check the degree of degrees of freedom for this displacement technique. So here the unknowns are 3. So we have to find theta B, theta C and theta D. And theta A is going to be constant. It is having the fixity. So theta B, theta C and theta D are the unknowns. So if we are finding these 3 unknowns, we can able to obtain the final answer using the end moment equation. So for starting the problem, we have to find the fixed end moments for span by span, for each span, and we have to establish it for establish the moments at either ends. So MAB, and we have to assume fixity on either side. You take the span AB, you assume fixity on either side, and 100 kilonewton concentrated load is provided. So FAB equal to minus WAB square by L square, minus 100. A is 4 meter, B is 2 meter square by L square 6 square, 44 kilonewton meter. FAB. FBA is plus WA square B by L square, 100 kilonewton load, A square is 4 square and B is 2 meter by 6 square. So this is 88 kilonewton meter. Next to span BC, assume fixity on either side. It is with UDL, minus WL square by 12, minus 20 L square by 12, minus 41.67. FCB plus WL square by 12, so 20 kilonewton. L square is 5 square by 12, so plus 41.67 kilonewton meter. And FCD, one side is overhanging, so it is sufficient to find the moment FCD. It is minus 20 into 1.5. Since it is a hogging moment, you can take minus 20 into distance 1.5 minus 30 kilonewton meter. So first step, we have to find the fixed end moments. And next we have to frame the slope deflection equation. The idea of slope deflection equation is fixed end moment followed by the moment due to the joint displacements. So we are just adding both the elements. For example, MAB for the first span, MAB equal to minus 44 is 0.4 is a fixed end moment, followed by the joint moment due to the joint displacement is 2EA by L, 2 theta A is a near end and B is a far end for MAB. So theta A and plus theta B. So here theta A gets 0. So the remaining solution is minus 44.44 plus 1 by 3 EI theta B by L. You substitute the corresponding span also. So that is about 6 meter. So if you simplify this, you can get the equation 1. Similarly, I am trying for the equation 2 on the other side of the span, first span. So that is MBA. That is FBC plus 2EA by L. MBA means 2 theta B. Theta B is a near end. So 2 theta B plus theta A. So you substitute the fixed end moments and simplify this. You can get the equation 2. MBC equal to fixed end moment followed by the moment due to the joint displacement. So minus 41.67 and 4 by 5, 2 EA by L and MBC. So 2 theta B plus theta C. And theta B, C will be there. It cannot get it will be there. We have to find the value. On the other side, MCB equal to FCB plus 2EA by L, 2 theta B, 2 theta C. C is a near end and B is a far end. So you add all the substitute L value and simplify, you can get the equation 4. MCD is very easy, just you multiply. We got the final moment MCD, so minus 30 kilonewton meter. No fixed moment, we got the moment load, final moment. So now we have got three theta B, theta C unknowns. So if you are having two unknowns, you need two boundary conditions. We can take joint displacement. Joint equilibrium condition says sum of the moments meeting at the joint is going to be zero. Sum of the moments meeting at the joint is going to be zero. So let us consider joint B. So the moment on either side, this is MBA and this is MBC. Sum of the moments meeting at the joint is MBA plus MBC. That's going to be zero. Next, you consider joint C. So MCB, MCD is going to be zero. So applying all the values in the two joint equilibrium conditions, you can get equation 5 and equation 6. And if you're solving these two equations, you can get what is theta B. And theta B is minus 32.67 by EI, and it is negative since rotation at B is anticlockwise. Theta C is 1.75 by EI, and it is positive. Let us take it as positive, is clockwise. So substituting these values in slope deflection equation, we can get all the final moments. MAB, you substitute EI theta B value and EI theta C value in these five equations. You can get MAB. The bottom diagram shows the final moments, which is written in red color. This is minus 61 anti-clockwise. MBA is plus 67.11. Similarly, MBC 67.11. So joint moments at the summation of joint moments get 0. Equilibrium condition is satisfied. Similarly, MCB minus 30, MCD is plus minus 30, MCB is plus 30. So if you know all these things, you can treat each and every span as a simply supported beam. You are converting it as a determinate structure. If you know the end moments, you can convert it as a determinate structure, and you find the reactions simply by taking sigma A0 or sigma B0. You can get all the reactions at the support. So RA and RB, first is one 32.31, RB is 67.69 kilonewton. Similarly, BC, RB is 57.42 and this is 42.58. And next RC plus 20, so the upward reaction is 20 kilonewton. So if you're finding these reactions, you can plot the bending moment diagram, and also we have to find the span moments. And 100 kilonewton non-centric load is acting, so you substitute WAB by L, you can get 68.26. And here the UDL is acting throughout the span, simply supported beam with UDL. So you take WL square by 8 as the span moment. So if you know all these things, this is simply this is free end, so moment 0. So if you know all this, if you know the span moment, and then end moment is 61, and this is 67.11, and this is 62.55. So you can get the remaining values, and finally you are getting the net bending moment, which is shown in the diagram. Similarly, you can plot the, based on the reactions, you can plot the shear force also. So RA 32.31, here 100 kilonewton load is acting, so 100 minus 32 will become 67, right? So again at this RB support, the reaction is you deduct what is the reaction and you plot the SFT for the remaining span. Thank you. So using this, you can this is a step for finding the RA and RB. So with this value only, the shear force diagram is plotted, and also we can obtain the maximum bending moment at the point. You can find where the bending moment crosses 0, that is the point of contraflexure, and by equating shear force 0, you can find the point, and also corresponding bending moment is also obtained in the point where the shear force gets 0. So that's going to be 15.26.